Now we come to the set project method in this lesson. This is, we've actually already secretly used that in the generating the sloping distribution. Is a very, very important method for, it's in fact the only method I know for doing complicated distributions. So here was this piece of Python. If you remember when I discussed this in the unit one, I pointed out actually here was a case where the enigmatic Python, which is here, was probably not as easy to understand as the rather mundane Java, which took many more lines, but it was rather clearer what was going on. And this is a very typical except project. You generate here uniform events, then you take each of those uniform events, and then you apply a test on it using another random number, which this test rand is a different, this is one set of random numbers, this is a different set of random numbers. You see whether you basically, if you want to, if you generate it here with this distribution, which is 1, you want to actually reduce the probability of events when the mass, say when the mass is 140, we're trying to reduce the 1 to 0.5, so this number here becomes 0.5 for mass, for the case where the base is 140. Well, this says here that we only accept this event with a probability when the number 0.5 is greater than the random number. This random number is uniform between 0 and 1, which says that we accept the event with probability R half. Therefore, we get on the average half as many events at mass of 140 as we do at mass of 110. So this is a very good example of the accept project method, very simple, and it's the general idea. You generate events, sort of you take the maximum value of the distribution, which is here 1, at which we happen to know at 110. You generate events according to that flat distribution. Then you look at the parameters of the event, which here case is only one number, the mass. Then you look at what the distribution, the relative probability you want, which here, okay, this is the relative probability. It starts at 1 at 110, goes to a half at 140. So it's 0.75 at 125. And then we take that, we calculate for each event what this actual distribution is, and then we test it against the randomness, and the totally independent random number. If it's bigger than the random number, we accept it. If it's less than the random number, we reject it. So here, if this number is, say, 0.75, and this is a uniform between 0 and 1, 75% of the time will accept this event, and 25% will reject it. So this is the accept reject method, and it's a universal way, which I used to use continuously for all sorts of distributions I used to generate. Because when I'm generating those physics events, they have the world's most complicated distribution. There ain't no way you can invert it and find probability and generate things according to that. So you always use this accept reject method. And that then gives you, of course, this result here, which is roughly twice as high here as it is here. Because of these being bin sizes, it's not exactly a factor of 2. Because, actually, this is really at 111, and this is at 139. So that ratio is not exactly 2. But this is, we discussed this as, in great detail, and this is what you get, this distribution from that code. So here's a little more refinement on that, which actually I used to use in practice. And it's used to generate random numbers. By this x actually is here written as an actual number, but in general, for the examples I used to, it's a complicated vector in all sorts of different dimensions. Then you generate your random numbers uniformly with x min and x max, and then you accept with a probability, which is f of x, the actual thing you want, the distribution you want, divided by the maximum. And sometimes actually it's very hard to find the maximum. And so actually what you need to do is you need to estimate the maximum. And this is what I used to do. So you then actually use that estimate, not the true maximum, and you'll find that it's perfectly fine as long as the estimate is whatever the estimate is. However, if the estimate's far off the real maximum, then you reject a lot of events which shouldn't be rejected, and so it's not so efficient. Whether that's important or not depends on how long it takes to generate the events. Anyway, this is the only possible way of doing for high dimensions x, and where f of x is very complicated because you can't do the integrals any other way. So this is the foundation of how to do random number generating vectors in a complicated space. So now we come and use these to do the so-called Monte Carlo method.